This is lecture 4C. We've talked about 5 different types of chemical reactions so far, and we're ready to start with number 6, which are acid-base reactions. These are very similar to number 5, which are precipitation reactions. Both are similar in that the reactants involved in the reaction are a pair of compounds. Compounds can be thought of having a positive and negative component, whether they're either ionic compounds or maybe acids, which have a hydrogen bonded to an anion. And in each of these different types of reactions, what happens is the two compounds swap their positive and negative partners. Sometimes they're called exchange reactions. And in an acid-base exchange reaction, what happens is the hydrogen from the acid combines with a hydroxide from the base, and it creates HOH or water. And that stable compound is what drives an acid-base reaction. So the reaction between an acid and a metallic hydroxide will produce water and be an acid-base reaction, as will the reaction between an acid and a metallic oxide, because when hydrogen and oxide bond, hydrogen being +1, oxide being -2, the product would be H2O. So acid-base reactions produce the stable molecule water, whereas reaction type number 5, precipitation reactions, when you switch the partners, you produce an insoluble ionic compound called a precipitate. So these reactions involve acids, and acids fit into 2 categories. There are strong acids, which are acids in which every single molecule releases a hydrogen ion into solution. And we've learned what acids are strong acids: HCl, HBr, HI. And then any oxyacid with at least 2 more oxygens than hydrogens in the formula, these would be considered strong. You put 100 HCl molecules in water, every single one of them ionizes into a hydrogen and a chloride. If we try to do a couple of examples of this last type of strong acid, oxyacids with at least 2 more O's than H's, if you look at the formula of an acid like this one, nitric acid, just count how many O's are in the formula, count how many H's, and subtract them. 3 minus 1 is 2. Because this acid has at least 2 more O's than H's, nitric acid is a strong acid. For sulfuric acid, there's 4 O's, 2 H's, 4 minus 2 is 2. This has at least 2 more O's and H's. Sulfuric acid is a strong acid. Perchloric acid has 4 O's and 1 H. That's 3 more O's and H. That means this is a really strong acid. And H2CO3 only has 1 more O than H. It shouldn't be in this list. It is not a strong acid. It fits into the other category, which are called weak acids. Weak acids are any acids in which all of the molecules do not release hydrogen ions in water solution. So that would be all other acids besides the ones we just saw above. So that means if you have something like carbonic acid, H2CO3, if you dissolve it in water, maybe 100 of them, 5 of them will release their hydrogen ions, but the other 95 will stay bonded together as H2CO3 molecules. So they don't produce a lot of hydrogen ions, therefore not a lot of ions in the solution. They don't conduct electricity very well, so they're considered weak acids or weak electrolytes. So let's look at some examples of acid-base reactions. Let's say we're mixing together solutions of sodium hydroxide and hydrobromic acid. Sodium hydroxide, NaOH, hydrobromic acid, HBr. 2 compounds. When you have 2 compounds, you switch the partners. Sodium goes with bromide, +1 -1 would be NaBr, and hydrogen goes with hydroxide, hydrogens +1, hydroxides -1, so HOH. When you have a polyatomic ion in an equation that you're trying to balance, if the polyatomic ion appears on one side and the other, treat it as a single element. So I'm writing water as HOH so I can utilize that phenomenon in balancing. There's 1 hydroxide, 1 hydroxide, 1 free hydrogen, 1 free hydrogen, 1 bromide, 1 bromide, 1 sodium, 1 sodium. This reaction is balanced. When they tell you you're mixing together solutions, that means the 2 reactants are both aqueous. For the products, you have to use your solubility rules. For sodium bromide, this is based upon Rule 1, which says all alkali metal ions or ammonium ions never precipitate with anything. So sodium's not going to precipitate with a bromide ion. This has to be an aqueous substance. HOH, of course, is the covalently bonded molecule water, which is really stable. Water at room temperature acts as a liquid. You would give it the phase liquid. So because you're creating a stable molecule here, this is what drives the reaction, much like for precipitation reactions, when you form an insoluble salt that's a solid, that drives the reaction as well. Anytime you have electrolytes in an equation, the molecular equation is not the final way you should write it. We're going to write it in ionic form, then net ionic form, because we want to write the electrolytes in their more common form or their more accurate form, which is dissociated ions. The sodium hydroxide, when it dissolves in water, separates into sodium ions and hydroxide ions. Hydrobromic acid is one of the strong acids we talked about just a moment ago. Every single HBr will ionize in water. It exists in solution as hydrogen ions and bromide ions. On the product side, sodium bromide is a soluble ionic compound, completely dissociates into sodium ions and bromide ions. And then HOH was the covalently bonded molecule water. Water exists as H2O. You could leave it HOH if you want, or write it H2O, but you definitely do not want to write it as hydrogen ion and hydroxide ion. Next time you drink a glass of water, think about what you're drinking. You're drinking millions and millions of water molecules. You're not drinking hydrogen ions and hydroxide ions. So once you have the ionic equation written, if you notice anything's the same on the left and the right side, those are spectator ions. The sodiums are the same on the reactant and product side, the bromides are. And if you cancel those out, what's left over is your net ionic equation. So the net ionic equation for this reaction is the hydroxide ion from the sodium hydroxide eventually finds the hydrogen ion from the HBr, and it combines to form water. Let's try another example. Let's say solutions of potassium hydroxide and hydrofluoric acid are mixed. Potassium hydroxide is KOH, hydrofluoric acid is HF. It's two compounds. You're going to switch the partners. The potassium goes with the fluoride, +1 -1 makes KF, and hydrogen goes with hydroxide, +1 and -1 makes HOH. This is another one where it happens to be balanced how it's written. There's one hydroxide on both sides, one free hydrogen on both sides, one fluoride on both sides, one potassium on both sides. The reactants were aqueous because it said two solutions are mixed. KF is an ionic compound that has an alkali metal ion in its formula, and from rule 1, they never precipitate, so that has to be aqueous. And you'll need to recognize HOH as water, which is a liquid. Because there's electrolytes in the equation, we're going to write it in ionic form. Potassium hydroxide, when it dissolves in water, breaks apart into potassium ions and hydroxide ions. HF is an acid, and with acids, you have to be careful. If in the last example, we had HCl, which is a strong acid that completely ionizes. But HF is not a strong acid, that's a weak acid. Only 5% of the HF molecules actually ionize, 95% don't. So if you only have one chance to write HF in an accurate ionic equation, because most of them do not ionize, we're going to write it as HF aqueous. So that's really only 95% right. It's 5% wrong because 5% of the time it's a hydrogen ion and a fluoride ion. But with only one way to write it, we always take the more common way that the substance exists, and it's as associated HF molecules. On the product side, KF is an ionic compound that's soluble. All soluble ionic compounds dissociate when they dissolve, and water's a molecule, H2O liquid. In this reaction, there's only one spectator ion, that's the potassium ion. So if you cancel those out, the net ionic equation here turns out to be the hydroxide ion from the potassium hydroxide will bump into the many HF molecules that are in the solution, and the F- will be formed, and an H2O molecule will be created as well. So that's one form of acid-base reaction. Another form of acid-base reaction is gas formation. So sometimes you'll just get water formed, but sometimes you'll get gases formed, and there's two specific examples I would like you to know. If you ever do an exchange reaction and you form the weak acid, carbonic acid, H2CO3, this will immediately decompose into water and CO2. So for this particular type of reaction, you just have to recognize if carbonic acid is being created as a product. That would happen if you were mixing together solutions of potassium carbonate and hydrochloric acid. Two compounds, potassium and chloride, would go together. +1 and -1 makes the formula KCl, not K2Cl. Hydrogen and carbonate would go together. Hydrogen's +1, carbonate's -2, so the formula has to be H2CO3. And so these would be your two products. If you want to balance the equation, we have two potassiums on the left side. Oh, let me say this first. I'm so sorry. So what we noticed was that we formed H2CO3 as a product in this reaction. Whenever that happens, you erase the H2CO3 and rewrite it as H2O plus CO2. That decomposition occurs, therefore a gas is produced, and that's what drives the reaction. This one you actually also get water as well. So two reasons that a reaction occurs. Now onto the balancing. 2 potassiums on the left side, a 2 in front of the KCl balances that. To balance the chlorines, we'll need a 2 in front of the HCl. That now makes 2 hydrogens on both sides. The hydrogens are balanced. We have 1 carbon and 1 carbon. For the oxygens, 3 oxygens on the reactant side and 1, 2, 3 on the product side, reactions balanced. The reactants were soluble in water, so they're aqueous. Potassium chloride is an ionic compound with an alkali metal ion salt, so they never precipitate with anything, so that has to be aqueous. The water formed is a liquid, and you should know carbon dioxide is a gas. So this is your molecular equation for the reaction between potassium carbonate and hydrochloric acid. Because there are electrolytes in the equation, you're not done. You have to write it in ionic and net ionic form. So all aqueous ionic compounds always dissociate into ions. And for K2CO3, because there's 2 potassiums in the formula, you're going to get 2 K positive ions and 1 CO3 2 minus ion. HCl is a strong acid that 100% ionizes. It'll ionize into a hydrogen and a chloride. With the 2 in front, however, you distribute that to both. So that actually produces 2 hydrogen ions and 2 chloride ions. On the product side, KCl, soluble ionic compound, they always completely dissociate. This will form a potassium ion and a chloride ion, but because there's a 2 in front, you get double the number of each. So 2 potassiums and 2 chlorides. And then anything that's not aqueous, it's already written in its most accurate form. Water's a liquid, carbon dioxide's a gas. In this ionic equation, we have 2 potassium ions on the left and the right. If there was 2 on one side and 1 on the other, something's wrong. You must have misbalanced it, so go back and check. And then we have 2 chlorides on the left and 2 on the right. They cancel out. So the net ionic equation that's happening is the carbonate ion from the potassium carbonate will eventually bump into the hydrogen ions from the hydrochloric acid solution to turn into water and carbon dioxide. How would you know that reaction occurs? Because you're going to see bubbles formed when this reaction happens. There's another type of gaseous reaction that occurs, and that's the formation of the gas H2S, which has a very characteristic odor to it. H2S is what you smell next to sewers and from rotten eggs. And so if this is ever formed in a chemical reaction, believe me, you'll know it. Let's do an example of where you would form H2S. Let's say you take crystals of iron 2 sulfate and then add them to hydrochloric acid. So crystals of iron 2 sulfate added to a solution of hydrochloric acid. So this is the first example where we've seen one of the ionic compounds not in the aqueous state. Iron 2 sulfide were crystals, that means it's a solid. But it's still 2 compounds. You're still going to predict the products the same way. So the iron 2 would go with the chloride, plus 2 minus 1 would be FeCl2, and then hydrogen go with sulfide. Hydrogen's plus 1, sulfide is negative 2, so the formula has to be H2S, and there's the gas that's produced. So because you're producing H2S gas, that's going to actually cause the crystals of iron 2 sulfide to react with the hydrochloric acid. To balance the equation, we're going to need to put a 2 in front of the HCl. That'll balance both the chlorides and the hydrogens, so we now have a balanced equation. If we write the phases for this, the iron 2 sulfide were crystals. That's a solid. Hydrochloric acid is a solution. And now we're going to be creating iron 2 chloride in this solution, so solubility rules will apply. Solubility rule 3, chloride ions never precipitate with anything except for silver, mercury 1, and lead 2. So this is not one of the exceptions. That means this will be soluble. And then H2S, I would like you to know, is that foul-smelling gas. So because there's electrolytes in the equation, we're going to write it in ionic form. Solid's already written accurately. The reason it's a solid is the ions are sticking together. Hydrochloric acid is a strong acid that will ionize, and with the 2 in front, you're going to get 2 hydrogen ions and 2 chloride ions. The iron 2 chloride is a soluble ionic compound, so that will dissociate when it dissolves. You'll produce 1 iron 2 ion and 2 chloride ions. And then the H2S gas molecule is already written in its correct form. You write it the same, H2S gas. In this equation, we only have 1 spectator ion, the chlorides, so the net ionic equation that's happening here is these crystals of iron 2 sulfide are reacting with the hydrogen ions from the hydrochloric acid to produce free iron 2 ions floating off into the solution, and then hydrogen sulfide gas, which you would detect with your olfactory nerve, or more commonly, your nose. So those are actually the 7 types of what I call obvious reactions. And if you look at handout 6, it actually goes through those 6 different types of reactions. I call them obvious because if you look at the reactants for each of the 7, it has to be that one type of reaction only. What's a composition reaction? A reaction between 2 elements. What's a replacement reaction? It's always the reaction between an element and a compound. What's a combustion reaction? Always reacts with oxygen. What's a decomposition reaction? Only one reactant. And then now recently we've talked about precipitation formation reactions, and then water formation reactions, and then gas formation reactions. Those are all examples of exchange reactions. They all have 2 compounds and they just switch partners. When you switch the partners, you will get a reaction occurring if you form either a solid, or you form water, or you form a gas. So I call these the obvious reactions, but there's going to be a couple more reactions we're going to learn that I call non-obvious, because if you try to predict what's happening, you look at it the first time, I usually find it's not intuitively obvious what's going on. So we're going to explore those next. One final point, if you do flip handout 6 over to the next page, these are the solubility rules that I've been referring to for most of this lecture. And then I also have the list of the strong acids at the bottom just to remind you. So let's go to the types of non-obvious reactions. We'll do one of them today. The first non-obvious reaction we're going to learn is called a Bronsted acid-base reaction. Bronsted acid-base reaction has a characteristic look like this. HA would be an acid, B would be a base, and you get some kind of reaction happening here, which we're going to explain in just a moment. Now, why is it called a Bronsted acid-base reaction? We learned the definitions of acids and bases earlier in the semester. An acid was a substance that releases hydrogen ions in a water solution. A base is a substance that releases hydroxide ions in a water solution. Those were actually called Arrhenius acids and Arrhenius bases. But 2 chemists, Thomas Lowry and Johannes Bronsted, came up with a probably broader, better definitions of acids and bases. I don't know why these reactions are called Bronsted acid-base reactions. I don't know what happened to Lowry. Maybe Bronsted was just so much better looking that he just got all the glory for this. I'm not really sure. But nonetheless, what they did is they expanded the definitions of acids and bases for a particular reason. And that is to account for the fact that NH3, which is ammonia, is a base. You dissolve ammonia in water, test it with litmus paper. The litmus paper turns blue, which is characteristic for basic solutions. The problem is, according to the Arrhenius definition of a base, it should have a hydroxide in its formula that it releases into the solution. And I'm looking really hard, but I don't see a hydroxide ion in the formula of NH3. So there had to be a reason why NH3 was a base. And Lowry and Bronsted came up with the conclusion that Arrhenius was too specific about his definitions and he needed to broaden them. So here's what they decided to define as an acid and a base. A Bronsted acid is defined as a hydrogen ion donor, and then a Bronsted base is defined as a hydrogen ion acceptor. So notice there's no mention of the hydroxide ion in here. Just so happens that a hydroxide ion is a really good hydrogen ion acceptor. But hydroxides aren't the only bases. Bronsted and Lowry expanded what bases were. They're anything that could accept a hydrogen ion. So let's see if we can look at a couple of examples here of reactions that are Bronsted acid-base reactions, and I'll show you why I call them non-obvious. Let's say we're going to mix together solutions of potassium bisulfate and lithium hydroxide. Potassium bisulfate, K, HSO4, and lithium hydroxide, LiOH. So if I give you this on the homework, the first thing you should do is go, oh, 2 compounds, switch the partners. Potassium goes with hydroxide, +1 -1 KOH. Lithium goes with bisulfate, because bisulfate's one of your polyatomic ions from the nomenclature quiz. Lithium's +1, bisulfate's -1, so LiHSO4. When you switch the partners like this, then if a reaction is going to occur, it's going to be because you either have a precipitate, which means precipitation reaction, you have water, which is an acid-base reaction, or you form a gas, which is also an acid-base reaction. If you look at our 2 products, I don't see water there. I don't see a gas. Let's test them with the solubility rules. KOH has an alkali metal ion in its formula, so that actually means it has to be soluble. Alkali metal ions don't precipitate with anything. And the second compound, lithium bisulfate, also has an alkali metal ion in its formula, so that means it's going to be soluble. So here's our problem. The reaction didn't appear to be obvious. There's no precipitate, no water, no gas. So this didn't work. So that means we got to erase those products and try a different plan. And so what we're going to do is something a little bit different. You know, when I was a kid, I saw a movie that was called Plan 9 from Outer Space. Probably the worst movie ever made. Some people might tell you that Troll 2 was a worse movie, but don't believe that. This one's really, really bad. And I've always wanted to work that somehow into the lecture for chemistry. And so I thought, no better way to actually use it than right here when you get to this point where you're switching partners, you don't get a precipitate, don't get water, don't get a gas. What are you going to do instead? You need a new plan, and that's going to be Plan 9 from Outer Space, and here's what it is. You are going to write the reactants in ionic form, and then you're going to scan over all those reactants and see if you can find a Bronsted acid and a Bronsted base. So here we go. The potassium bisulfate is a soluble ionic compound that will dissociate into a potassium ion and a bisulfate ion. The lithium hydroxide is a soluble ionic compound that will dissociate into a lithium ion and a hydroxide ion. So these are the four ions that are floating around in the solution. And if the reaction wasn't intuitively obvious because we didn't make a precipitate, water, or a gas, maybe we're going to have an acid-base reaction here. You have to find an acid or a base. So the Bronsted acids are things that give up hydrogen ions. So what could be a Bronsted acid here? Well, you could have the hydroxide ion that has a hydrogen in it. Maybe it gives that up. Or it could be the bisulfate ion because that has a hydrogen ion in it. So there's theoretically two possible acids. But I would like you to know that according to Arrhenius, this was the chemical species right here that causes solutions to be basic. So the hydroxide ion is never going to be the substance to give up a hydrogen ion. That's going to actually always act as a base. So therefore, the HSO4 minus must be the acid. So just by looking at these four individual ions in the solution, the HSO4 must be the acid, and then the OH minus must be the base. They're what are reacting. The potassium ion, not doing anything. The lithium ion, not doing anything. Those are actually spectator ions. Just cancel them out and don't even use them. The reactions between the bisulfate ion and the hydroxide. The definition of a Bronsted acid is it gives up hydrogen ion. This hydrogen ion, the plus, leaves there and comes over here to the hydroxide. So if you lose a H plus, you become SO4 2 minus. If hydroxide gains an H plus, it becomes H2O. So when you mix these two solutions together, the bisulfate ion and the hydroxide ion actually exchange a hydrogen ion between them, forming a sulfate ion and forming water. And that's the non-obvious reaction that occurs. Let's try again. Let's say solutions of ammonium chloride and potassium hydroxide are mixed. Solutions of ammonium chloride and potassium hydroxide. If you were to look at that, you should immediately go, oh, switch the partners. So ammonium would go with hydroxide, +1 -1 makes NH4OH, and potassium would go with chloride, +1 -1 makes KCl. I don't see water over there on the product side. I don't see a gas. I see two ionic compounds. From the solubility rules, the first one has to be soluble. It has an ammonium ion in its formula, and rule 1, ammonium ions never precipitate with anything. The second one has a potassium ion in it. Alkali metal ions don't precipitate with anything. So once again, we came up with a situation where there's no water, no gas, and no precipitate. If that's the case, these are not the products for the reaction. Immediately erase them. And if you want to figure out what really happens, you have to go to Plan 9 from Outer Space. And so that means you're going to write the reactants in their dissociated form. So the ammonium chloride would be written as an ammonium ion plus a chloride ion, and the potassium hydroxide would be written as a potassium ion plus a hydroxide ion. And now you scan through this and you look for what could be an acid and what could be a base. And the hydroxide is sticking out like a sore thumb. That is a basic species. Hydroxide will be the base. So the only thing that can possibly be the acid is the only other substance in the equation that has hydrogens in its formula, which would be the ammonium ion. So that's going to be your acid. The hydroxide ion is going to be the base. That means the other two ions that are in the solution aren't doing anything. They're spectator ions, cancel out the chloride, cancel out the potassium. The reaction will just be between the ammonium ion and the hydroxide ion. And the way the Bronsted acid-base reaction occurs is the acid gives up a positive 1 hydrogen ion over to the base. That means this turns into the neutral molecule NH3. This turns into the neutral molecule H2O. The NH3 is actually a gas. It does dissolve in water. You could write AQ for the phase of that. That would be okay. But that gives you a telltale indication that this reaction is really occurring, because if you waft the solution, you're going to actually detect the smell of ammonia there being given off as this reaction proceeds. Let's do one final one. This one's going to be a little bit more challenging. Let's say we take gaseous ammonia and bubble it into a solution of sodium bisulfate. Gaseous ammonia bubbled into a solution of sodium bisulfate. This is two compounds, so you would want to switch the partners. The problem is NH3 is really not an ionic compound, so it really doesn't have a positive and negative component. So to make this exchange reaction work, we're going to have to use our oxidation number rules and figure out what's the positive component, what's the negative component. The hydrogens have the lowest electronegativity of all nonmetals, so that's going to wind up being assigned a positive 1 oxidation number because its electronegativity is so low. And if they're each positive 1, the nitrogen is going to be negative 3. So notice they're sort of written in reverse order. The positive is second, the negative is first. So the positive hydrogen is going to have to go with the negative bisulfate. So a hydrogen that's +1 with a bisulfate that's -1 would make HHSO4 or H2SO4. The sodium is the positive component here. The nitrogen is the negative component. Sodium's +1, nitrogen is -3, so the formula has to be Na3N. A little tricky, but these would actually be the products if you really just exchange the positive and negative components of the two compounds. H2SO4 is an acid, so that's not going to be a precipitate. And NH3 is an ionic compound that has sodium ions as the cation, and sodium ions never precipitate with anything. So both of these are soluble substances, and there's no water and there's no gas formed as well. So once again, we've done the exchange reaction, but been unable to predict a type of chemical reaction that is known to occur. So if that's the case, erase those products, they're wrong, and you have to do plan 9 to try to figure out what reaction's going on here. So to do the reaction, we're going to take the reactants and write them in ionic form. Writing things in ionic form apply to strong acids and to ionic compounds. We're definitely going to take the sodium bisulfate and dissociate into a sodium ion and a bisulfate ion. But this really is not an ionic compound. It's a molecule like water or carbon dioxide. So when it dissolves in water, it stays as a molecule. So you do not break that into hydrogen ions and nitride ions. It's an NH3 molecule. But the sodium bisulfate does dissociate into a sodium ion and a bisulfate ion. So here are each of your reactants. Now, the HSO4, good candidate for the acid because it has a hydrogen there, but theoretically the ammonia can be an acid as well. But if you remember back to why we have definitions of acids and bases that have been improved by Bronsted and Lowry, it's because the compound ammonia was known to be a base. So that means I really want you to know two things that are bases in solutions. One is the hydroxide ion, the other is the ammonia molecule. That means the HSO4 minus must be the acid, and in this case, the NH3 is acting as the base, and the sodium ion's not doing anything, so get rid of it, it's a spectator ion. So the reaction that occurs is going to be between the gaseous ammonia, which is bubbled into the solution, and the bisulfate ions. And the reaction is the acid gives up its hydrogen. So this is the acid, the hydrogen ion comes off of there, leaving an SO4 2 minus, and the hydrogen ion sticks onto here, forming NH4 with a +1 charge. And that's how you predict the products for the non-obvious Bronsted acid-base reactions.